Hi, welcome to another video on MOSFETs. So in this video we'll see the design of few amplifiers and their simulation also. So consider this circuit. So as you can see, this circuit is a CD amplifier. So this is a CD amplifier. Uh, the specifications are as given here. So we are expected to get a voltage gain of 0.82, and we are asked to find the values of R2, Rin, Rout, and it is also asked to plot the input and output waveforms, and we are asked to find what is the maximum input voltage that we can apply to this amplifier. Now to start with, so let us write all the equations that are relevant to this circuit diagram. So let us start with the voltage gain expression of this CD amplifier, which is given by GM RS by 1 plus GM RS. So this is the expression for the voltage gain. So let us write what is the expression for GM, which is 2ID Kp into W by L. So we know this, and we know the expression for ID also, where ID is half Kp W by L VGS minus VTO whole square. And from this, for this circuit diagram, we can write the expression for VGS as VG minus Vs, because source voltage is not ground, so that's why I'm writing it as Vs. So the voltage at gate is nothing but VDD into R2 by R1 plus R2. The voltage at source is nothing but ID into RS. So it is ID into RS. So this is equal to VGS. So these are the equations we know, and with the given values, given specifications, we can, using these equations, we shall find these unknown parameters. And of course, we also know the Rin, the input impedance of this amplifier. Of course, input impedance of this amplifier. Okay, let us write the expression. Maybe during the process, we will also write the small signal model and try to understand what is Rin and all those stuff. It is R1 parallel to R2, which is nothing but R1 R2 by R1 plus R2, or we can write it as R1 inverse plus R2 inverse, and it is full inverse. So these are different ways of calculating the value of Rin, and of course the Rout happens to be the resistance seen from this output node, which will be Rs in parallel with 1 over Gm. So these are the equations that what we know for this particular circuit diagram. So now let us start solving these equations and try to get the relevant values. So if you consider this equation 1, in this equation 1 I know this AV, so we know this RS, so we can find what is GM is. So from this equation 1, so let us find the GM value, so which can be easily found. Is this fine? Or okay, let me just put this as the position. So now it is 0.82 alpha equals, open the parenthesis, it is alpha A into 800 divided by, open the parenthesis, 1 plus alpha A into 800, sorry, it's 800, close the parenthesis, one more closure, shift cal. So we'll get the value of GM. The value of GM would be, so it is coming out to be 5.69 millisiemens. 5.69 millisiemens. So it is now 5.69 millisiemens. So this is 5.69 millisiemens. So that's what is the value of GM. So using this GM, so let us use equation 2. Here we know what is GM, so we know what is KP, we know what is WL. So let us find what is ID is. So now in this, using second equation with the known value of GM, let us find what is the value of ID. So it is now, so I can use this equation. It is 5.69 exponential minus 3 alpha equals under root of, open the parenthesis, 2 into 2 into, okay, I'm just looking for the best position so that you all can see this effectively. Just a minute. It is better now. It is 2 ID. ID is alpha A, 2 ID, and then we have KP is 200, sorry, into 200 exponential minus 6 into WL is 50. That's what is this expression. So close, shift cal, shift cal. So I'll get the value of ID. So ID is 1.61 milliampere. So we got the value of ID now. So now once we know the value of ID, so let us use this equation. Here we know this ID, we know KP, we know WL, we know VTO. So we want to find VGS. So let us use equation 3 to find the value of VGS. So VGS comes out to be, so it is 1.61 exponential minus 3 alpha equals, it is 100 exponential minus 6 into 50 into alpha A minus 0.4 whole square. Oh, there is a mistake. Into, it is the mistake. Shift cal, shift cal. That's one. So one of the value of VG, one of the value of VGS is coming out to be minus 0.167 volt, which is not a possible answer. So let us try to find the other answer of this. The other answer would be equals 1 equals shift cal. So it is coming out to be 0.967 volts. So this is the possible answer. The VGS is now 0.967. So this is the value of VGS. So now uh, let us use equation 4 to know the value of VG. So we know what is VGS, which is 0.967, and we know what is VS. So VS is how much? VS is ID into RS. So we can know what is VG is. So using equation 4, let us find what is VG, which is nothing but 0.967 alpha equals alpha A minus, of course, how much is VS? VS is nothing but ID into RS. ID into RS is 1.61 exponential minus 3 into 800. Shift cal, shift cal. So I got the value of VG as 2.255 volt. This is the value of VG. So let us okay, in this expression, of course, let us not use the entire equation. Let me just use the equation where Vg is equal to VDD R2 by R1 plus R2. So here we know what is Vg now. We know what is Vg. We know what is VDD. So we know what is R1 also given as 300 kilo ohm. So we can find the value of R2. So what is the value of R2? It is now 2.255 alpha equals, it is of course VDD in this case we have taken test 3.3 into alpha A divided by 300 exponential 3 plus alpha A, shift cal, shift cal. So I'm getting the value of R2 as, so it is 647.36 kilo ohm. is the value of R2. So we got one of the value of the equation that need to be found, which is nothing but 647.36 kilo ohm. Then we are supposed to find what is R in, which is nothing but the parallel combination of 300k and 647k. So let me make that. It is 300 of course you can simply make 300 exponential 3 inverse plus I'm using this, so I'm just using this thing. So it is, sorry for, let me just, I think by this time you're all used to this calci, so you just this is 300 k and 647 exponential 3 inverse equals whole inverse is 204. So R in is 204.9 kilo ohm. This is what is the value of R in. How about the value of R out? R out is nothing but how much is RS? So RS is 800 inverse plus how much is 1 over GM? So GM, we know this is this much. So 1 over GM is, let me just make this. Can I write this as RS inverse plus GM whole inverse, because 1 over GM is already there, so it simply becomes GM plus 5.69 exponential minus 3 close the parenthesis whole inverse is just a minute. Oh, I have now, I didn't open. Let me just make this 800 inverse plus 5.69 close whole inverse is oh sorry, I didn't put milli there, so let me put milli here. So this is milli, this is exponential minus 3 close the parenthesis and inverse. So now it is 144 ohms. 144 ohms. So this is how you can do this. So this is the value of R out. So in this expression or in this problem, we found the value of R2 as 600 and the found out values are R2 is equal to 647 kilo ohm and R in is 204 kilo ohm. I'm just writing the approximate values, and R out is 144 ohm, 144 ohm. And then next we are asked to find the input and output waveforms and what is the maximum input voltage that we can apply. So for that, let me draw. So now shall you write this as the possible swing of your output signal from 0 to 3.3 volt is the maximum swing that is possible. So now since the output is measured here, since the output is measured at this point, the drop here is, so how much is Vs? Vs we actually found it to be, so let us find how much is it. It is 1.61 exponential minus 3 into 800. It's actually 1.228. So Vs is 1.288 volt. So that's what is this. Assume that this is 1.288 volt. So this is your reference point where your output will want to swing. Next, let us consider input voltage. Let us consider input voltage V in, which is actually going like this. It's around 0. It is around 0. It just goes like this. See here. This is okay. Let us not apply any signal here. So for some time, then let us apply a signal like this. Let us apply the signal like this. So this is my input signal. Initially 0 for some time t1. So after t1 it is applied. Now, what is the corresponding output? So when you don't apply the input voltage, the output is at 1.288 volt till you don't apply the signal. So till here it is the same. Then the output follows the input. That's what the name for this another name for this amplifier is a source follower. So since the source follows the input, it is called as source follower. Since it is the source follower, the source voltage, the output voltage follows the input. So now as your input is increasing, the output also goes the same way. Output also goes the same way. You can see, suppose if I draw this as my reference points approximately, so it goes like this. This is how it is. This is how it is going. So this is my uh, input the signal. This is V in, this is V naught, this is V naught. Now when I say V naught, it is the small signal. Now what is this amplitude? Okay, let us take an amplitude of 100 millivolt peak, 100 millivolt peak here. Then how much is this peak of your output signal? So it is 100 milli multiplied by the gain. The gain is 0.82. Gain is 0.8. So it will be 82 millivolts. It will be 82 millivolts. Now, how much? Okay, now this is the thing. Next, this is the output waveform. Then we have asked to find what is V in max that is possible. What is the maximum input voltage you can able to apply? What I mean to say is, suppose if you increase the amplitude of your signal, so does your input amplitude, it goes like this? So will it go like this and like this also? So does it mean that your output will also go up and then come down here? Come down here. Now if you can see how much is the space, how much is the voltage swing that is available. The voltage swing available is 1.288 volt from this reference down to here. How much is the voltage that is available from here to here? So you actually have 3.3. From there it is 3.3 minus 1.288. How much you have? You have 2 point, here it is 2.012 volt is the space available here. But out of this, can you see this MOSFET should also always remain in saturation. So how much is the VDS that is required to keep the MOSFET in saturation? Let us find what is VDS sat. So how much is VDS sat? It is nothing but VGS minus VTH. How much was VGS? So VGS was 0.961. 0.967 minus 0.4, it is 0.567. So out of this 2.012 volts, so let me dedicate how much voltage. This is the voltage you cannot enter, which happens to be this entire, okay, so you are supposed to not to enter this 0.567. So if it is 0.567, then how much is this voltage? It is 3.3 minus 0.567. So it is 2.73. 2.73. Your output can go on the positive side, not beyond 2.73, not beyond 2. Suppose if it goes beyond 2.73, then the MOSFET enters the linear region. So then, even though you have a swing from this to VDD as 2.02 volt, not the entire voltage is available for swinging, because that includes this voltage also. So let us find the effectively available swing on the positive side from 1.288 to 2.73. So it is now 2.733 minus 1.288. So you actually have 1.445 volt as the swing available. So for this output voltage to swing, on the bottom side you have 1.288 volt for the output signal on the bottom side. On the top side you have 1.445 volt available, which is not symmetric. Then what is the maximum voltage swing that is possible? Because if you go beyond this 1.228, it will going to cut here, so which will going to distort, which will going to make your waveform distorted, it will get clipped off. So V0 max possible is minimum of these two voltages. So what is we want to write, it is minimum of 1.288 and 1.445, which is the minimum of these two. So this is one swing available on the bottom side, on the bottom side, on the negative side. On the top side you have this much swing available. So then what is the maximum V0 max, V0 max, okay, let me say V0 max you can have. So V0 max I can have is 1.288 volt. So this is the maximum voltage you can think of having. So now if this is V0 max, then what is V in max that is possible? V in max that is possible. The V in max possible we can find out from AV is equal to V0 by V in. Is this the equation what we have for AV, which is V0 by V in? So what we'll do is we'll write this also as V0 max by V in max. V in max. So then, so what is then V in max is equal to? V in max is equal to V0 max by AV. How much is V0 max available? It is 1.288 volts. How much is AV? 0.8. So how much is input maximum possible? It is 1.288 divided by 0.8. How much is this? This happens to be 1.57 volt is the input maximum you can apply. If you apply less than this, it's fine. If you apply any voltage which is less than 1.57, then the output voltage will be within this available swing. If you try to apply more than 1.57, then what will happen? It will clip here on the bottom side. Maybe on the top side it may be fine because you have more swing. So V in max is 1.57 volts. 1.57 volts. So let us do a simulation of this particular circuit and try to understand, okay, all these theory what we learned, is it fine or not. So for which let me start this. So let me have a new circuit. Let me start with a new circuit. So this is, I'm just doing it for, let me do it from the scratch. Let us take a NMOS transistor. Where is that? Okay, that is there. Okay, it's there at NMOS 4. Where is NMOS 4? It's here. And then let me, okay, let me adjust the dimensions of this as, because WL is 50. Let me take